Welcome to Maths with EJD. In this video, I'll be talking about generating functions in population modeling. That's application of generating functions in population modeling. But of course, that's under the broad idea that generating functions can find application under physics and biology. So let's go for that. Generating functions are powerful tools. I've said that a couple of times. They are powerful tools in biology and physics for solving problems involving growth, recurrence, and dynamic systems. Dynamic systems. So they provide a structured way to model and solve real-world problems like population dynamics, and particle distribution. So having said this, let's consider an example that is in biology, which is about population growth. So let's talk about population growth modeling in biology. Okay, so we have this interesting question that a population of rabbits grows according to the recurrence relation P of n equals 2p into n minus 1 plus 1, where p of 0 is equal to 1. Okay, so with that, we aim to 1, derive a formula for p of n using generating functions. 2, want to calculate the population after specific generations. Say n is equal to 0, 1, 2, 3, and 4. So from the beginning to the fourth generation. And 3, finally, want to analyze the long-term behavior of P of n. Okay, so that's the question right there. Let's go on now and deal with that. Okay, so the first thing we want to do is to, of course, the recurrence formula is really important. So we say given P of n, that's the recurrence formula, which is 2p into n minus 1 plus 1, with P of 0 equals 1. That's like a starting value. So the first thing we want to do is to define the generating function So we say let g of x be the generating function for the sequence p of n. So that means that g of x is equal to summation from n equals 0 to infinity for p of n, for p of n, x raised to power n. Okay, so with that done, substituting the recurrence relation, that's we have to put the recurrence relation here. Substituting the recurrence relation, Pn equals 2p into n minus 1 plus 1, and then we multiply by x raised to power n and sum over all n. Okay, so that's the next thing we have to do. So that means that we need to evaluate something like this. G of x equals summation from n equals 0 to infinity of p of n, which is now 2p into n minus 1 plus 1. All this multiplied by x raised to power n. Okay, so that's actually what we need at the end of the day. But before we get there, um, let's tackle these things one after the other. I mean, we can have it this way generally, and then we can also write this out. We have p of n equals 2p into n minus 1 plus 1. That's what we have. So we can now go term by term so we can now have a summation from n equals 0 to infinity p of n x raised to power n. So automatically this is g of x, and this will now be equal to summation from n equals 0 to infinity of 2p into n minus 1 plus 1 multiplied by x raised to power n. So we can have it this way. So we can get everything term by term. So with this done now, then we move ahead and we can shift the index for consistency. So of course, clearly, I guess I want to switch back. Clearly, this is g of x based on our definition from the very beginning. This is g of x. So that's settled. Then next, we have to deal with this part. To do that, so this is g of x now, which will be equal to, so this term is a bit tricky because it is not n directly. It is 2p into n minus 1. So in that case, we are going to have because of so by the time we sum this, we sum 2 over the whole thing, we can bring out 2 from there, and that will be like 2 times x multiplied by the summation from n equals 0 to infinity, okay, of of pn of p of n, which is x raised to power 1 now. So that goes for that part. Then for this constant, so, if we do this summation for this constant, we have, I guess what I should have even done is to split it up first. So we can go step by step. So it can be more understandable. Summation from n equals 0 to infinity of 2p. In fact, this p can go out, but it's okay. So 2p into n minus 1, x raised to power n, okay, plus summation from n equals 0 to infinity of just x raised power n because of this plus 1 now. So we have split it apart like that. And if that is the case, then it means that we can then go ahead and do the next thing. So g of x now will be equal to um so we have 2. So this whole expression is going to give us 2x summation from n equals 0 to infinity of p of n x raised power n. Now, it means that this minus 1 now, so it's like uh, a step backwards. And because of the step backwards, that's why we have this x jumping out of this. So we have a step backwards. So we have 2, which is the constant, and this x, and then we have this summation now, plus this again, which is summation from n equals 0 to infinity x raised power n. Now, we already know what this one looks like. This is like x raised power 0 plus x raised power 1 plus x raised power 2 plus x raised power 3. That's like 1 plus x squared. That is simply the geometric series we have come across a lot. Okay. So we can then go on and say this is g of x equals 2x g of x, because now this is g of x. Then plus this is now 1 over 1 minus x, because it's geometric sequence. We've seen that a whole lot before now. So this is the expression we have. And at the end of the day, we need g of x like that. So that means that we now have g of x minus 2x g of x equals 1 over 1 minus x. So here, g of x is common. So we have g of x into 1 minus 2x, and that is equal to 1 over 1 minus x. Okay, so that we now have g of x. If we divide through by 1 minus 2x, we have g of x equals 1 over 1 minus x into 1 minus 2x. So, I mean, this looks familiar. It's the kind of thing we've seen previously. So here we need to apply, we can now, we want to look for, what is it called now? We are looking for, we need to break this up, split this up into partial fractions. So splitting up in partial fractions. I think okay, let me do it to be sure what the values are actually. So we have g of x will be similar now to g of x. Okay, well, let me put it this way. Splitting up the right-hand side, actually. Splitting up the right-hand side into partial fractions, This is the step we have to follow. 1 over 1 minus x into 1 minus 2x. And that is similar to a over 1 minus x. They are both linear. B over 1 minus 2x. Okay, we've done something like this before now. So the next step is to multiply through by the LCM. Multiply through by the LCM. Of course, the LCM is 1 minus x into 1 minus 2x. Okay, I need to make that a bit better. 1 minus x into 1 minus 2x. So if we do that, on the right-hand side, we have 1, and that is equal to, on the left-hand side, we have a into 1 minus 2x plus b into 1 minus x. Using the cover-up method, if x is equal to 1, we can easily eliminate this. So we have 1 equals a into 1 minus 2 times 1 plus b into 1 minus 1. So this is 0. It automatically goes away. So we have a equals 1 minus 2 is minus 1. So a is minus, sorry, 1. 1 is equal to minus a. That implies that a is equal to minus 1. So we keep that. A is minus 1, right? I think that works. So after that, we can then go for the next one. We can say if if A is now, based on this now, if A is half, if X is half rather, we can eliminate A. So if X is equal to half, then we can have 1 on this side, and this is A into 1 minus 2 times half, okay? And coming to the other side, we have plus B into 1 minus half, okay? So this is 1 equals A into half. 2 times half is 1, so we have 1 minus 1 plus B. 1 minus half is simply half, so this can go because 1 minus 1 is 0. So we have 1 equals B over 2. So if you cross multiply, B is equal to 2. So we have our values right there. So our G of X now, so we can then say therefore 1 over 1 minus X into 1 minus 2X is equal to, it's the same thing as A is now minus 1, I believe. Yeah, A is minus 1 all over 1 minus X, and B is 2. That's 2 all over 1 minus 2X. So of course, we can rewrite that to make sure we don't have minus first. So 2 all over 1 minus 2X minus 1 over 1 minus X. So that is it. So we can say, therefore, G of X is equal to 2 all over 1 minus 2X, okay, minus 1 over 1 minus X. But we have to write it as a summation like we always do, right? So we have to do that right now. In that case, then we go for, we have to do the quick stuff. We have 1 minus 2X. Okay, I mean, I can still write this properly. So we have 2 into 1 minus 2X raised by minus 1 minus 1 minus X raised by minus 1. So we can actually get them in form of summation. So I'll just do the quick thing I do, 1 minus 2X raised by minus 1. So we just go get the first three or four times to see the pattern. So this is 1 raised by minus 1 minus 2X raised by 0 divided by 0 factorial plus minus 1 raised by minus 2, that's minus 1 minus 2X raised by 1. So that minus 2 plus 1 can always be the highest power, minus 1 all over 1 factorial plus the next one, that's minus 1 minus 2, 1 raised by minus 3 minus 2X raised by 2 all over 2 factorial, and all of that goes on like that. So the first one is always 1 because 1 raised by minus 1 is 1, minus 2X raised by 0 is 1, 0 factorial is also 1. So coming here, we have 1 minus 1 times 2X, that's simply 2X. And coming here, 2 factorial cancels 2. And then we just simply have 4x squared. 4x squared. I think we've seen this before, and that goes on like that. So if you look at the pattern, this is more like having n x. So it's more like having, this is more like 1x raised to power 0 plus 2x raised to power 1 plus 4x raised to power 2, 4x raised to power 2, and so on and so forth. So if you look at the pattern, the first term is 1, the second term is 2. So it's more like we have, what can we say here? This is power 0, right? So this is more like 2 raised to power 0, x raised to power 0, plus 2 raised to power 1, x raised to power 1, plus 2 raised to power 2, x raised to power 2. So, I mean, the pattern is formed. So we can see the pattern clearly now. So this is more like summation from n equals 0 to infinity of 2 raised to power n, x raised to power n. That's what that clearly looks like, okay? So we have this part sorted. So we need 1 minus x. We need 1 minus x raised by minus 1, which we have also seen before. So we have 1 minus x raised by minus 1. Again, that's 1 raised by minus 1 into minus x raised by 0 all over 0 factorial plus minus 1 comes down, 1 raised by minus 2 minus x raised by 1 all over 1 factorial plus minus 1 minus 2, 1 raised by minus 3 minus x raised by 2 all over 2 factorial, and the rest like that. So the first one is always 1 for obvious reason. 1 raised by minus 1 is 1. Minus x raised by 0 is 1. 0 factorial is also 1. So here we have plus x, and coming there 2 factorials cancels, and we have plus x squared and all the rest. So the pattern is clear also, because this is simply x raised power 0 plus x raised power 1 plus x raised power 2, and it goes on like that. So that means that we have that to be summation from n equals 0 to infinity of x raised power n. Basically, that's what we have for that. So in that case, we can go back to the original g of x. So we can now say, therefore, g of x, which is equal to 2 g of x, which is 2 into 1 minus 2x raised power minus 1 minus 1 minus x raised power minus 1, okay, that we had up there. Yeah, that. So that would simply be 2 summation. What did we have? Yeah, 2 raised power n. 2 summation from n equals 0 to infinity of 2 raised power n, x raised power n, okay, minus what we just had, summation from n equals 0 to infinity of x raised power n. So this is our g of x now. This is simply the g of x we are looking for. This is our generating function. So the first part of the question is taken care of. The first part is to find the generating function. The second part says to calculate the population after specific generations, say n equals 0 and all that and all of that. Okay. Um, okay. I mean, the coefficients of xn are very instructive in this case. The coefficient of xn gives Pn, okay? Because we need to calculate the Pns, right? The second set to calculate the population after specific generations, okay? Okay, so to calculate the populations after generations n equals 0, 1, 2, 3, and 4, for instance. Now, in that case, we need to get the value of Pn, right? And that can only be obtained from the coefficient of what we have. Okay, so we can say, okay, let me go back. So from g of x, from g of x, which we already know is 2 summation from n equals 0 to infinity of 2 raised power n, x raised power n, plus summation, that should be minus now. So minus summation from n equals 0 to infinity of x raised power n. From this, we can rewrite this as summation from n equals 0 to infinity of 2 into 2 raised power n, x raised power n. So we can write this as plus summation from n equals 0 to infinity. Now, the essence of this is that we need the coefficients. This is like minus 1 into x raised power n. Okay, so these coefficients are really useful for us. That's why I'm doing this right now. Okay, so because we need to extract Pn from this place now. So the coefficients of x raised power n in g of x gives the Pn we have now. The Pn now is 2 into 2 raised power n, x raised power n, right? Minus, no, we don't need the x raised power n anymore, right? In fact, I should write this better. Let me write it in a better way. So this is more like, yeah, I mean, we can even do it in a smarter way. So this is 2. If 2 raised power 1 multiplies 2 raised power n, we have 2 raised power n plus 1. So we can do it that way. And this is x raised power n. So now the coefficients of x raised power n in gx will now be 2 raised power n plus 1 minus 1. Okay. Just this one directly now. Minus 1. So with that, now we have our population. So what do we do? we can now begin to substitute these values one after the other. So we can now have P of K. I guess I want to change now. So we can now have P of 0, that would be 2 raised power 0 plus 1 minus 1. That is 2 minus 1, and that is simply 1. So the population of rabbits after the first generation is 0. I mean, is just 1. At 0 generation, we had just one rabbit. Well, I don't know. These things also have to make biological sense sometimes, but this is a theoretical thing, right? So the next thing is population after one generation. That's 2 raised power 1 plus 1 minus 1. And that is 2 raised power 2 minus 1. That is 4 minus 1. So after one generation, after the 0th generation, we have 3 rabbits. Okay, that's what that is about. And then if we go to 2, we have p raised power 2, p of 2, that's 2 raised power 2 plus 1 minus 1. That's 2 raised power 3 minus 1. And that is simply 8 minus 1. So 7 rabbits after the second generation. And then we go to p of 3. So P of 3 is equal to 2 raised power 3 plus 1 minus 1. That is 2 raised power 4 minus 1. That is 16 minus 1. So 15 rabbits after the third generation. And for the last one, of course, we can keep going, but the last one we will have here is 4. So we have 2 raised power 4 plus 1 minus 1. That is 2 raised power 5 minus 1, which is 32 minus 1. So after 4 generations, we have 31 rabbits. Okay, we have 31 rabbits. Okay, now that is the second part is taken care of already. That is starting from, yeah, this is where the second part started from. Okay, the first part started from here. The first part started from, yeah, I've numbered it already, 1. So we want to analyze the long-term behavior of P of n. That's number 3 now. Okay, 3. For the long-term behavior, for the long-term behavior of P of n, okay, we know what we have is so for the long-term behavior of P of n, you know that the P of n we have extracted is this, right? So we have P of n equals 2 raised power n plus 1, 2 raised power n plus 1 minus 1, right? So the long-term behavior is like what is going to happen at infinity. So that means that we have to take the limit as n approaches infinity, as the generations go far. So that'll be limit as n goes to infinity of 2 raised power n plus 1 minus 1. Okay, so from here now, uh, so from here we have, of course, when you have um limits like this, the rule of thumb says substitute directly. So that means we're going to have 2 raised power infinity plus 1 minus 1. That means 2 raised power infinity minus 1. And at the end of the day, that is just undefined. And there's no better way to do this, right? So that simply tells us that the population is going to grow exponentially. That's what the indication there is about. So we see that as n approaches infinity, that at least as the generations increase, the dominant term, the dominant term, which is 2 raised power n plus 1, the one that has the n, 2 raised power n plus 1, all right, dictates, let me write that properly, 2 raised power n plus 1 dictates, it dictates the growth, okay, dictates the growth. Thus, the population grows exponentially, grows exponentially with base 2, exponentially with base 2. Okay. So the generating function, we can see now that we have answered all the questions actually. So you see that the generating function allows us to find a closed form expression for the rabbit population then we're able to predict growth rates and compute specific values, just like you've seen. So in this example, we see how generating functions simplify solving recurrence relations and provide deeper insights into growth dynamics. Now, the original expression we had was this long thing, which is this 2p, p of n is 2p into n minus 1 plus 1. But using generating functions, we're able to get a closed form solution, which we're able to latch onto, and that is this one now. This is the closed form solution. And with this, we're able to do so many things about the population. So that's one application of generating functions in population modeling. So in the next video, which I think is about the last video as far as generating functions is concerned in this series, except if something else comes up along the line. I'll be talking about generating functions as it is applied to cryptography and data structures. Because cryptography has something to do with cybersecurity, which is like a hot cake these days. All right. So you don't want to miss out on that. So be sure to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. And of course, you want to comment, let me know how helpful these videos are for you. And at the same time, let me know if you have a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep enjoying maths. Bye.